Okay, welcome to our next lesson in complex numbers. What we're going to do today is look at calculating powers. We'll start with powers in this lesson. Powers of complex numbers using something called de Moivre's theorem. And how exactly does this work? Excuse me, how does this work? If you think about something even as simple as a binomial, if I wrote down x plus 3, that's a fairly simple binomial. But what if I raise that to a power, a large power, like, well, let's say 6? Now, I don't know if you realize how much calculating there would be to actually, multiply all that out. It's not just x to the 6 plus 3 to the 6. That's not what it would be. You'd actually have to multiply x plus 3 by itself 6 times. That is a long calculation. That's an incredibly, well, not really calculated or complicated, I suppose, but it's long enough. Well, what if you had a complex number raised to a large power, such as 3 plus 5j? All right, now that's in rectangular form. But what if that was raised to the power of 8? That is long. You'd have to, it's like taking a binomial and multiplying it by itself 8 times. Now, I'm not saying you can't do it, but it would take you quite a while to do that. Well, fortunately, if your complex number is written in polar form, there's a much simpler way to do it using something called de Moivre's theorem. Now, note what I just said. If it's written in polar form, de Moivre's theorem applies. You cannot use de Moivre's theorem if your number is in rectangular form. Interestingly, there's also a derivation of it that you can use if your number is in exponential form. The exponential form explains why de Moivre's theorem works. If I just gave you a monomial like 3x squared, and if you were raising that to the power of 4, what would you actually do to evaluate that? What would actually happen? Well, the 3 actually does get raised to the power of 4. All right, the number in front does get raised. But what happens to the x? The x is squared. Well, if you use your power of a power rule, they would actually be multiplied, wouldn't it? So that would become x to the power of 2 times 4, which is 8. Well, if you can do that with exponents, that explains why the exponential form it works, and it also explains why de Moivre's theorem works with polar form. It's basically the same rule. Let me show it to you carefully. If you have a number in polar form, there's your r in front. There's your theta. Remember, it's in degrees for polar form. If you're raising that to the power of n, just like we saw a moment ago for a monomial raised to a power, the number in front, like the coefficient, that does get raised to the power of n, but the angle itself gets multiplied by n. And that's de Moivre's theorem. It's actually a very, very simple way that you can raise any complex number to any power, really. So let's look at example number 14 here. It says, use de Moivre's theorem to solve. Actually, that should be to evaluate, but okay, let's play their game. Now, notice this time the number is actually in rectangular form. Well, that's a little bit of a drawback because to use de Moivre's theorem, it has to be in polar form. Well, let's do our calculation. We have to get our r. So that would be the square root of a squared plus b squared, which in our case is 2 squared plus 3 squared. And so that's 9 and 4. So that's the square root of 13. You could actually leave it the square root of 13 if you wanted to. That would be the exact form. But if you didn't leave it the square root of 13, it would be approximately 3.61. Okay? Notice I'm using 2 decimal places. Now, getting theta, notice that this number, this complex number, if you were to graph it, would end up in quadrant number 1. So fortunately, when you calculate your reference angle, that will be theta in this case. So theta is equal to the inverse tangent of b over a, which in our case is 3 over 2. Make sure your calculator is in degree mode for this, by the way, although this would also work for radians. Make sure it's in degree mode. And I get 56.3 degrees, I do believe. Yeah, that's what I get, 56.3 degrees. So in other words, this number, 2 plus 3j to the power of 3, is the same thing as 3.61, your angle symbol, 56.3 degrees, and you raise that to the power of 3. Now we can apply de Moivre's theorem. So this becomes 3.61 to the power of 3, and the angle becomes 3 times 56.3 degrees. And now, so this would become equal to, let me just write it here, 3.61 to the power of 3, I get 47.0, angle symbol, and 168.9 degrees. Okay, so there it is. That's the answer in polar form. But unless the question says to leave it in polar form, I mean, that is your answer in polar form. That is that complex number raised to the power of 3. If the question does not say otherwise, you need to convert it back into the form that the original question was in. The original question was in rectangular form. So again, unless it says to leave it in polar form, I now must convert that back into exponential form. And remember how we, or not exponential, sorry, into rectangular form. Remember how we do that. A is equal to r times the cosine of theta. There's my r, and there's my theta. And b is equal to r times the sine of theta. And if you do that here, you're actually going to end up with, let me just write it down, you're going to have approximately negative 46, it actually comes out really, really close to 46, plus 9j. All right, that's what you would get. Now you could write some more decimal places to that if you wanted to. And by the way, don't forget, if you have a calculator that can actually do complex numbers, you could actually type that into your calculator to verify that this will be your answer. All right. Okay, let's look at example B. B is actually going to be easier to do because example B is already in polar form. In fact, if you wanted to, you could even write it in the abbreviated polar form. Your R is 0.2, that's your R right in front. And there's your theta. You see, it's in both places, in both locations. So angle symbol 35 degrees. You're going to raise that to the power of 4, it says right there. Okay, so using de Moivre's theorem, the R actually does get raised to that power. Angle symbol 4 multiplied by 35 degrees. And so voila. And again, you can leave the answer in polar form because the original question's in polar form. And what I get is 0.0016. So it's a small r. It's in front, very small. And 4 times 35 degrees, I'm pretty sure you're going to get 140 degrees. Now, you can leave your answer looking like that, even though it doesn't quite look like the original problem. It's in polar form. You can expand it if you want, but it's quite okay to leave it like that. C is also in polar form, raised to a power. So using de Moivre's theorem, this would become 2 to the power of 8. Now that's going to be fairly big, but remember, just use your calculators for that. Angle symbol, 8 times 135 degrees. So 2 to the power of 8. I'm pretty sure that's going to give you 256. And the angle, 8 times 135 degrees, is 1,080 degrees. Okay, well that looks pretty good, right? Not quite. There's a little something wrong with that. Not wrong, but there's a form that's not quite correct. Remember that when you write a number in polar form, a complex number, the angle theta should be between 0 and 360. Your final answer should have that for your angle. Well, that angle is too big. It's too large, 1,080 degrees. Now, it's not wrong, but the correct form would have theta between 0 and 360. So what we should do is come up with another angle that's equivalent to 1080 degrees, but smaller. And those are called coterminal angles. So what you have to do is just take your calculator, take your 1080, and subtract 360 from that. And just use your calculator for that. See what you get when you subtract 360, and I think you're going to get 720. Well, that's still too big. So take your calculator and you subtract 360 once again. You always subtract 360s. Okay, if you end up with a negative angle, by the way, you add 360. So anyway, that brings us down to 360, which technically is still too big because remember, theta should be less than 360. So if you subtract 360 from that one last time, ta-da, look at that, you get 0 degrees. So the correct answer in the correct form would be 256, angle symbol, 0 degrees. Now that would get you your full marks. That would get you your full marks. Now the first one, don't forget, is not wrong. It's just that the form is not correct for theta. So there is your final simplified answer. And that, ladies and gentlemen, is how you can raise any complex number to a power using de Moivre's theorem. So there's some really good examples now on page 25, practice number 14. Again, use de Moivre's theorem to evaluate, that should say. Okay, A and B are in rectangular form, so you have to do a conversion first, like we did up here. You have to convert them into polar form first. Then use de Moivre's theorem on the polar form. And because the question does not say leave your answer in polar form, we'd have to convert those two back into rectangular form. A little bit of work, but it's not that hard. Just a little bit long. C, well, those two are in polar form. It's the expanded polar form, but that's okay. You could write it in the condensed version if you like. And E and F are automatically in the condensed polar form. Don't forget, if your angle is over 360, you need to bring it down. You need to get it under 360. Okay, so you try those with E and F. And I'll finish there for today. In our next lesson, we're going to be basically doing the same thing. We're still going to be using de Moivre's theorem, but we're going to be using it for not powers, well, not integer powers, but we're going to be using it to find roots, like square roots, cube roots, fourth roots of complex numbers. And that's fairly interesting as well. Okay, so I'll stop there for today. Have yourselves a wonderful day. Bye-bye.